Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Stepping inside as we jump into sections 3.1 to 3.4 in the Big Ideas Math Integrated Math 3 textbook, a quiz review, I believe they're called. And 3.1 was on graphing polynomial functions. 3.2 had adding, subtracting, multiplying polynomials. A lot of things you actually saw in IM2. Section 3.3 was on dividing polynomials using long synthetic division, and 3.4 was factoring polynomials. Again, a lot of something you saw in IM2 with some extra things on top of it, right? Obviously, that's why we're doing the IM3 material. So this quiz is 17 questions in total. I'll be going over them. Check the description section down below if you'd like to download this PDF, as well as find a very specific problem 1 through 17 that you would like to cling on to and get a solution guide. Get a solution guide for her. Without further ado, guys, we'll go ahead and get started with it. Decide whether the function is a polynomial function. If so, write it in standard form and state its degree, type, and leading coefficient. Now, believe it or not, this was a part of the graphing polynomial stuff in section 3.1. So questions 1, 2, and 3, we have this. So f of x equals, and like I said, this is something that you possibly knew also in IM2, but we're going to heavily hit on why we use this stuff a little more so, a lot more so later when we graph again, after we learn some more things about how to get everything within a graph that we want. So we don't have to use tables. Although here, if we have to, I don't know if we have to graph. Here, if we do, we might have to use tables. All right, f of x equals 5 plus 2x squared minus 3x to the fourth minus 2x minus x cubed. Our goal is to get this in standard form. That's the first thing, and that can help answer anything else we need. Everything is, simplified, but we have certain degrees of these numbers. We kind of look at the exponents. For example, this x is squared. That's of degree 2. This x is to the fourth is degree 4. You can't see it, but there's an implied 1 right there. That's degree 1. This is degree 3. How about this constant? It's degree 0. You could imagine if there was an x to attach to it, it would be x to the 0 power, and x to the 0 power is 1. So we rewrite these in descending order of degree. We want to go 4, 3, 2, 1, 0. Keep the signs as they are, or as they were. So negative 3x to the fourth takes the lead, takes charge, and then minus x cubed plus 2x squared. Oh no, that's just a random x. Plus 2x squared minus 2x and plus 5. Doesn't matter what the coefficients. Whoa, what happened to my font? Doesn't matter what the coefficients in front were and all that. Just matters what the degrees of the things are. What was this? Plus 2x squared minus 2x plus 5. Good start, Mr. Robinson. Perfect. Okay, standard form. We have it. There we go. What else do they want? Oh, decide whether it's a polynomial function. Yes, it is. Yes, it is. Now, what makes something a polynomial function? It's that each term has variables with whole number exponents, and 0, 2, 4, 1, and 3 are all whole numbers. Negative numbers are not whole. Fractions and decimals are not whole. Irrational numbers, such as square root of 2 and pi and things like that, those are not whole. Counting from 0 onward, those positive integers are whole numbers. This makes it a polynomial function. So when I said yes, I mean yes, polynomial. So hopefully that's okay. All right, we rewrote it in standard form to state its degree, type, and leading coefficient. Now the degree of this is degree 4. That's based off the leading term only. Type is based off the degree. A degree 4 polynomial is known as a quartic polynomial, not quadratic, quartic. And then the leading coefficient, I'll just put LC. The leading coefficient is the coefficient for the leading term, which is negative 3. That leading term matters a whole lot when it comes to our graphing, especially, given this sign and really whether this is an even or odd number. Those are two big things we'll do with graphing down the line. All right, number 2. G of x equals 1/4 x cubed plus 2x minus 3x squared plus 1. Once more, we are being asked whether or not this thing's a polynomial. I'd like to go ahead and state this term by term. Is this a monomial? Yes, it is. This is a whole number 3 as an exponent. It's okay that this is 1/4. This can be any number you want, as long as that is a whole number exponent for the variable. Plus 2x, that's 2x to the first power, minus 3x squared, whole number, right, 2, plus 1, 1 being a constant, degree 0, we're all good there. So is this a polynomial? Yes, indeedy. So me putting yes again is for whether or not it's a polynomial. So if so, we continue forward on the next things, which is rewrite in standard form. So let's begin with that. The 1/4 x cubed, that is still the leading term. Degree 3 is highest. This is degree 3, 1, 2, and 0. All we really got to switch is these two right here. Minus 3x squared plus 2x. And then we got a plus 1. So here's our standard form. I don't know if I abbreviated that last time or wrote that out, but that's okay. So identify their standard form. We need the degree. It's a third degree polynomial. Third degree polynomial is also known as a cubic. Think cubed, right? X cubed. And the leading coefficient this time is 1/4. Now, it's a fraction. That might mean some sort of vertical compression thing, but most importantly, really for us, actually, is that it's a positive number when it comes to graphing things. Okay, number 3. H of x equals, we got F, we got G, now we got H. H of x equals 3 minus 6x cubed plus 4x to the negative second power plus 6x. Now we have a good monomial here of degree 0 and degree 3. This is degree -2, which, what does that mean? Remember, -2 may be an integer, but it's not a whole number by mathematical definition. And it's not that that part matters, it's that the degrees need to be 0 or positive as whole numbers. That's a -2. Keep in mind, if this were a rewrite of this problem, it would be this plus this, plus 4 over x squared. And then plus that. That's rational. That's not polynomial. This is a no when it comes to, is this a polynomial or not? It is not, and this guy is the one that's breaking it right there. I should really put that in red, but that's the thing that's making it mess up. Really, again, you just have to look at the degree of this being a -2, and that kind of tells all. Now, it says if it's a polynomial, rewrite in standard form, all that stuff. This isn't. I'm not saying there's no benefit to rewriting this in descending order of degree, but they're not going to ask more about this. It's not a polynomial. So the ideas and conventions that we have in place for what we want to do with a polynomial, whereas when this is a rational term instead, doesn't apply. So we leave it. We're going to move on. Number 4. Also out of section 3.1, describe the x values for which part A, f is increasing or decreasing, part B, f of x is greater than 0, and part C, f of x is less than 0. So we have a graph on number 4. Let me copy and paste this one. It might be a little blurry because this is a very small one I'm copying from. I should grab, if this is not detailed enough, I think that's fine. Okay, so for part A, we're trying to decide where this is increasing and decreasing. Now we're asking for intervals on x. When you see this parabolic state of probably a quadratic function here, at x equals 2 is the axis of symmetry, and it not only shows where points reflect across, but it shows where points are the same height, where you have to go up to hit those points and go back down to hit the points. We are increasing to the left of to the left of 2 as we move to the right, and as we continue to the right, we start decreasing as we go downward. So we are increasing on the interval when x is less than 2, all those values, and we are decreasing on the interval where x is greater than 2. Again, we're asking on what intervals of x are the y values going up versus down. That's what's being asked there. That's part A. Part B, they're asking for what values of x do we have positive y values. F of x is greater than 0. We have positive y values when x is what? Here are the positive y values here. Right here, right here, right here, right here, right here, right here. Boom, boom, positive. Now at 1 and 3, the y values are 0. Not positive, but 0. But to the right of 1 is when we start being positive, and just up until 3 is where they end being positive. So from 1 to 3. So we can write that as a compound inequality. X is between 1 and 3. X values between 1 and 3 give us positive y values for this function. And they're not asking for the equation, but if we had the equation, we could plug in those numbers and see exactly that. So when is x less than 0? When is it negative? Almost everywhere else but the positives and 1 and 3 themselves. These ones are the negative. Let me erase those. Whoopsie, I guess not. Let's do it that way. There we go. Over here to the left of 1, we have negative x values, and to the right of 3, we have negative y values, I should say. To the left of 1, we have negative y values. To the right of 3, we have negative y values. So that's when f of x is less than 0. When x is less than 1 and x is greater than 3. We can put the and we have to keep them separate. Don't make it a compound inequality in this way where it says between two things, because it's not. It's actually a split of those two things there. All right, let's move on to section 3.2 base questions. It doesn't look like we're actually graphing on that review, which is kind of okay. Again, those graphs almost required lot of table usage, and I'm not saying tables are bad, so to speak, but we're going to find other conventions of graphing polynomial functions of higher degree, where a table's not really the crux of what we're trying to find. So maybe save it for the bigger chapter review. All right, number 5, write an expression for the area and perimeter for the figure shown, section 3.2. So we have this guy. Let's copy and paste it. We have, to me, well, they say area and perimeter. Let's see. Let's do perimeter first. How about that? Perimeter, we have to find out what all these lengths are as a whole. We have x plus 3 there, so this can also be written as x plus 3. This is x plus 1, and this is x. When you add them together, both x's combine to 2x. So 2x plus 1 over here. And then right there, this guy's also x. You know, if you're really savvy with this stuff, then you'd understand perimeter doesn't change whether you go this way and that way, or whether you go this way and that way. Meaning, I could really just combine this and double them up and be good. But let's just go on the nature of what you do have, because they will matter for area. So the perimeter of this, let's add all around here. We got 2x plus 1 as a whole, plus, I'm going to call it as it is right now, 2x plus 3, plus x plus x. Yeah, that's 2x, but plus x plus 1 plus x plus 3. X plus 1, x plus 3. Really, it's all one set of things for which we're going to combine, but 2x, 4x, 5x, 6x, 7x, 8x, and 1, 4, 5, 8. 8x plus 8. And that's the expression. So I'm simplifying that for perimeter. Area, we have a couple options in what we can do. One is either take this guy here and subtract out this guy here. Let's look at that one first. So for area, we can take the base times height of this. Remember that whole thing's 2x plus 3. So take 2x plus 3, multiply it by this height of 2x plus 1. And then we can subtract the area that will be this one, this x times x plus 1. This is an option for us. X plus 1. So let's try that one out and simplify it. I'll show you a second option you can do. And you can kind of make your choice on what you prefer. If I FOIL this thing out, I get 4x squared plus 2x plus 6x plus 3. And then minus, now whether you put this in parentheses or not, it's up to you. Just make sure you subtract both portions. So x squared plus x inside the parentheses. When you distribute the negative, they'll both be subtracted. Minus x squared minus x. So when you combine like terms, this will become 3x squared plus 7x plus 3. And that's multiplying polynomials, some combining like terms things. That is our area of this guy. And that's one way to do it. What's a second way to do it? Let me shrink this down so I can fit out a second way. I hate when grouping that does that. Now it looks a little weird, but that's okay. So there's one version. Now what's a second version? A second version is we can add the two smaller versions of these rectangles that you see here. There is dividing this up into this. We can take this rectangle plus this rectangle, for example. So those two separate areas. Let's try that one. Make sure we still get the same answer when we simplify everything. 3x squared plus 7x plus 3. All right, this bottom one has a base length of 2x plus 3 and a height of x. So let's do, I'll put the x first. X times 2x plus 3. And then let's add this red one. The red one has a height of x plus 1 and a base of x plus 3. So x plus 3 times x plus 1. And let's FOIL, or distribute this one. 2x squared plus 3x plus, now this is FOILing, x times x is x squared, plus 1x plus 3x is 4x, and then plus 3 times 1 is 3. So 2x squared plus x squared is 3x squared. 3x plus 4x is 7x. And then plus 3 is there. So 3x squared plus 7x plus 3 is our area. And look, we got the same area as before. So either or works when it comes to that area. And like I said, with perimeter, you could have treated it as just one large rectangle here because your distance around the object doesn't change just because you go that way instead of the other. But still the same answer. Or still the same work, I should say, getting to that answer. Okay, let's go to number 6. 6 through 8. Perform the indicated operation. This is still a part of section 3.2. We look at subtraction, multiplication, and another multiplication. Now on number 6 with the subtraction, again, very IM2 based things that we had done. We are subtracting one quantity from the other quantity. Now these quantities are wrapped around parentheses. The leftmost quantity has really no effect if I remove them. They're multiplied by 1, but these are multiplied by -1. Distribute the negative, as you just saw from the previous problem, number 5. Distribute that negative, this becomes a plus, and this becomes a minus. So all those signs change in the right quantity, whereas these stayed the same. And now we combine like terms. And if you noticed from the very first set of problems, they asked about standard form. If you've kind of been following along, you notice that I keep things in standard form like this. So 7x squared minus 3x squared, boom. 5x doesn't combine with anything, boom. And -4 minus 1 is -5. This is the simplified version of that problem and in standard form. It's a quadratic and all that. Number 7. We have a trinomial times a binomial. We got x squared minus 3x plus 2 times the quantity 3x minus 1. This is where we have to do larger distribution. My personal preference is to multiply binomials this way just to show you the visual. Multiply 3x by these 3 things here. Draw your arrows if you like to. And then multiply -1 by those 3. That way nothing really crosses over. So I'm going to go that way with it. Hope you don't mind. You can do either or. You're going to get the same result. 3x times x squared is 3x cubed. 3x times -3x is -9x squared. And 3x times 2 is 6x. Now -1 multiplies with these as well. We get -1x squared plus 3x minus 2. Remember, it's a -1 that multiplies to all 3. Now you combine like terms with that. 3x cubed minus 9x squared minus x squared is -10x squared. Plus 6x plus 3x plus 9x, and that minus 2. There is the simplification. We got a cubic. We got a cubic, people. Number 8, we have 3 binomials multiplied. The general rule for this, to not mess up, and just to do it in probably the best fashion, is just do 2 at a time. Don't try and do all 3 at the same time. Don't try and outsmart the problem either. You'll get it wrong if you try and do all 3 at the same time. Just do 2 at a time. I'll do the last 2 at the same time so I can front a binomial here. So I'll keep the x minus 1 just hanging and chilling. Over here, I got x squared minus x minus 12 by foiling. Now the x gets to distribute into these 3 and the -1 gets to distribute into these 3, just like the previous problem we have above. So x times these will just increase their degree by 1. We get x cubed minus x squared minus 12x. Then -1 times these 3, just change all their signs. -x squared plus x plus 12. X cubed is still at the front. Find your x squareds. These subtract together, become -2x squared. -12x plus x is -11x, and the plus 12 is right there. We are good to go. Almost halfway done with the review. Obviously, later problems might be longer, but number-wise, we're getting near it. Number 9, use Pascal's triangle or the binomial theorem to expand x plus 2 to the 5th power. I'll kind of show you sets of both when it comes to what we actually write out. Let me start with the binomial theorem. It's normally one that I wouldn't tend to do in these cases. Pascal's triangle to the 5th row is pretty clean. Now, the theorem in and of itself, I forget what letters they use for everything. I'll try and pretend like I know. But if you have, again, they might use P and Q, A and B. I'm going to use A and B because we've been using it. For A plus B to the n power, what you do here is, oh gosh, I'm not going to write this very well, am I? Okay, I don't think I'm going to write the formula because the thing is, I don't think you'll be helped by seeing it. I think it's saving you more than me. I'm going to pretend like that's the truth. Anyway, so for this thing here, here's what we're going to do. We start with the fact that there will be 6 terms. There will be 6 terms. The first term has a coefficient that's going to multiply in front, coming from 5, choose 0. In the next term, we're going to use 5, choose 1, and then 5, choose 2, 5, choose 3, 5, choose 4, and 5, choose 5. You can let your calculator do this for you if you want to. There's a formula for that. Otherwise, you can use the other version with Pascal's triangle, which I'm going to do next. 5, choose 0 is going to multiply by the first term raised to the 5th power times the second term raised to the 0 power. Now, these numbers should always add up to 5. And what's going to happen on the next thing is this is going to go down by 1. This is going to go up by 1. So plus, let me write it vertically for now, plus 5 choose 1 times x will be raised to the 4th power and 2 will be raised to the 1st power. plus 5 choose 2 times x to the third power and 2 to the second power plus 5 choose 3 times x to the second power times 2 to the third power. That's a 3. Plus 5 choose 4, almost done. No, this isn't the final answer, but times x to the first power times 2 to the fourth power plus 5 choose 5 times x to the 0 power times 2 to the fifth power. Now, I generally don't do it this way. I would do this more so if I need to find a single term, or if the Pascal's triangle gets way too big later down the line. These numbers can get pretty large, and I think I know most. Wait, is it 1, 5, 10, 10, 5, 1? I need to think beyond. I think so. I think so, because 1, 6, 4. Yes. Okay. So 5 choose 0 is 1. 1's going to multiply by x to the fifth, and then 2 to the 0 power is 1. And then 5 choose 1 is 5. Again, let your calculator work with you on that. And x to the fourth times 2 to the first is 2. And then we have 5 choose 2, which is 10. And then we have x cubed times 4. And then 5 choose 3 is also 10. These are actually, by the way, this combination stuff, it's going to go down like that. X to the second power and 8. And then 5 times x to the first times 16. And then 1 times x to the 0 power times 2 to the fifth. Whoop, 32, not 23. Okay, now when we, not combine like terms, but when we rewrite it as a whole binomial expansion, 1 times x to the fifth is just x to the fifth, plus 5 times 2 is 10, so 10x to the fourth, plus we got 40x cubed, plus 80x squared, plus 80x plus 32. And there's your final result. That's using the binomial theorem to work on combinations to get it right. What you can also use, and it's going to be the same premise as all of this. The difference is we won't really use the combination sets to build them. We'll use something called Pascal's triangle to build and get these exact same numbers right here. I'll show you how to get them. This next part remains the same as it was. I will conceal some parts that are unnecessary to work out, though. For example, writing out something to the 0 power or writing the first power in general. And then, of course, I'm going to have these numbers in play. Ones will be irrelevant. So you're going to see me hide a few more things as I go on. That's not a measure of using Pascal's triangle in place of this. That's just showing, as you do these problems more often, what you can probably skirt by. But let's build Pascal's triangle together. Pascal's triangle looks like this. Row 0 has just the number 1. Row 1 is 2 numbers, 1 and 1. Row 2 has 3 numbers, 1, 2, 1. Now, what you're building off of this is ones will always go down the pyramid on the left and right like that. And any numbers in the middle will be the child of 2 parent values that are the sum of those values. 1 plus 1 is 2, like that. And we continue down. So over here, and I'm going to get rid of these arrows in a bit. But going down here, 1's on the outside. This will have 4 numbers now. In between 1 and 2 will be 1 plus 2, which is 3. And symmetrically, you'll have also 2 plus 1, which gives you 3. And this continues. So let's get rid of the arrows. Let's keep going. Remember, this is row 3. Row 0 is the top one, and that's important for several reasons, including your use of combinations, including your use of binomial expansion, and all that stuff. So even though you want to call it the first row, it ain't. If it helps, the one with the 2 in it and the 3 in it, etc., will also help indicate what row you're in. So row 4 is 1, 4, 6, 4, 1. And row 5 is 1, 5, 10, 10, 5, 1. Now this being row 5 is the one that I was referring to. So the reason why we choose row 5 is because we are raising our thing to the 5th power. So x plus 2 raised to the 5th power means we're going to have 6 terms. Each term, as they go along, will multiply by the following coefficients. These coefficients are also 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, 5 choose 5. Maybe you didn't know that, but maybe you know Pascal's triangle with it. So let's do the same thing. X plus 2 to the 5th power equals. So we'd start with 1 times x to the 5th times 2 to the 0. I can just write that as x to the 5th. I think most every time you're going to kind of see that you're just raising the first term to the 5th power. And in the last term, you're just going to raise the 2 to the 5th power, right? Plus, now 5 is going to multiply by x to the 4th, which multiplies by 2 to the 1st power, right? You saw that before, but this time I'll just write the 2. So cleaning up things a little bit here. Plus 10 times x cubed times 2 squared, plus 10 times x squared times 2 cubed, plus 5 times x to the first times 2 to the fourth plus 2 to the fifth. 2 to the fifth. So that's me doing maybe a little less writing and things in general if I know how to calculate those parts. All I now need to do is multiply that coefficient by the number that 2 represented. So the final result should be the same as before. This is 10x to the fourth, 40x cubed, 80x squared, and 80x, and 32. So either or you can get to that result. Hopefully you pick and choose which one you like more. I generally like this one more, depending on what we're doing with the problem though. Because I know most of Pascal's triangle, and if I don't know the exact numbers, I can build that really fast. Once you just understand you're adding numbers, it's really no big deal to keep working it out. All right, let's go to number 10. Divide. This is section 3.3. Divide 4x to the fourth minus 2x cubed plus x squared minus 5x plus 8 by x squared minus 2x minus 1. Before I do it, let me... I can't use synthetic division. I was thinking I could in this one if that thing could factor, but it can't, so I can only give you one way to do this problem, okay? So we're going to do 4x to the fourth minus 2x cubed plus x squared minus 5x plus 8 divided by x squared minus 2x minus 1. Now we're hamstrung by long division. As long as this isn't a linear factor, you can't use synthetic division, and long division is really just the way you'd want to go with it. So let's do this. This is our dividend. No placeholder terms to speak of. It's written in standard form. That's helpful to you. Here's our divisor. We're going to figure out how many times the leading term in each kind of go into each other. How many times does x squared go into 4x to the fourth? It goes in 4x squared times. Because x times 4x squared is 4x to the fourth. Negative 2 and negative 1 will also multiply by the 4x squared, and we'll subtract this bottom result from what's up top. Negative 2x times negative 4x squared is negative 8x cubed. Negative 1 times 4x squared is negative 4x squared. So we'll subtract this result. Now, and as well as the book, I was surprised by this, I don't write subtraction, I just will do subtraction. So trust me on what I say for it out loud, but 4x to the fourth minus 4x to the fourth is 0. It cancels out. That's expected. That if you don't do that right, if that didn't happen, you didn't do something right. Negative 2x cubed minus negative 8x cubed. I know there's a minus there, but we're subtracting the negative. That becomes negative 2x cubed plus 8x cubed, which is 6x cubed. X squared minus 4x squared minus negative 4x squared is x squared plus 4x squared, which is 5x squared. Negative 5x minus 0, 8 minus 0. Okay, let's do it again. Let's keep going until we cannot put x squared into any term. That means that you have a degree lower than 2 over here. And if anything remains, that will be the remainder, which I fully expect a remainder. X squared goes into 6x cubed 6x times. X squared times 6x is 6x cubed. Negative 2x times 6x is negative 12x squared. Negative 1 times 6x is negative 6x. Let's subtract the result. These go away. 5x squared minus negative 12x squared is 17x squared, because of course it's addition. This is also addition, and you get 1x, and you bring down the 8. Now, this is my own visual style of this. Please choose a visual style for you that will make you get the answer correct. This is just a solution guide for my own personal doings. X squared goes into 17x squared exactly 17 times, and we go ahead and multiply these out. 17x squared minus 34x minus 17. Le cancel and le addition from subtraction of le negative. We get 35x, and also addition is plus 25. So the ultimate quotient is 4x squared plus 6x plus 17. X squared cannot go into 35x because this is a smaller degree than that. So this is your remainder that you're looking at right here. Your remainder. So your final result of this thing uses these two things together. This divided by this equals 4x squared plus 6x plus 17 with a remainder of 35x plus 25. But we don't just write those. The remainder is the portion of the fraction that couldn't divide out. So it is still a fraction itself, dividing by our divisor that we had. So the x squared minus 2x minus 1. Okay. No synthetic division to be had there. I imagine we're going to hit synthetic division a little bit later here. Oh, we're already jumping to section 3.4. Do we go back? Maybe we don't. Oh, sometimes we use synthetic division on these problems, so I'm not worried. We'll see. Number 11. If not, go ahead and check out the 3-3 stuff on synthetic division. Factor the polynomial completely. We have a cubed minus 2a squared minus 8a. I begin with seeking common factors, and I indeed have one with a, where I'm left with a squared minus 2a minus 8. This quadratic trinomial is one of those basic factorization types where you have two binomials that multiply together. We got to find two numbers that multiply to make negative 8 and add to negative 2. Those are negative 4 and positive 2. This is the final complete factorization of number 11. Number 12, 8m cubed plus 27. This is what is known as a sum of two cubes. It's something I suppose you must recognize on your own. Keep in mind, now that we're outside of the individual section, this can be a question shown up out of the blue on your assessments at any time. They're not saying, hey, find the sum of two cubes, or maybe they are. But consider this to be looking like some sort of a cubed plus b cubed. Now, it is if you recognize what two things are being cubed. We're cubing, on the right side of 27, we're cubing 3. We're cubing a 2 to get 8, and we're cubing m to get m cubed. So here's your a, here's your b. Now, a cubed plus b cubed factors into the following. A plus b times a squared minus ab plus b squared. This is the factorization of a sum of two cubes. So this will factor into a plus b times a squared minus ab plus b squared. So to simplify that, 2m quantity squared is 4m squared. Negative 2m times 3 is negative 6m, and 3 squared is 9. Now, as I've said a lot in the particular section itself, I know that this thing looks like maybe it's factorable, the same way that we could factor something like that, right? Bottom line is, in a sum or difference of two cubes, in any conventional version of these, you're not going to be able to factor that, period. It's not factorable. Don't try. You're done. You're done. Number 13. Z cubed plus z squared minus 4z minus 4. In instances like these, 4 terms, we got a cubic and all. No common factors, by the way, for all terms. We're looking to factor by grouping, which is pairing off consecutive terms such as these. As long as we're in standard form, it should work out the way you're looking for it to be. And because they built the problem for you, you can factor by grouping. Not every quadrinomial can be, but this one can. Factor by grouping says find the common factor that exists in this pair of terms and the common factor that exists in this pair of terms. What should remain inside the quantity, if factorable by grouping, is the same exact value. Z squared is a common factor there. You're left with z plus 1. You can factor a negative 4 out of here to get z plus 1 inside here as well. If these two aren't the same, you don't continue. Either it's not a problem for factoring by grouping, or you messed up, or both. But z plus 1 is a common factor out of both these terms. You can factor it out. Z plus 1 pulls out of both of those. You're left with z squared minus 4 from the other quantity. Now, you would be done, except z squared minus 4 is a special case of a difference of two squares. A squared minus b squared is z squared minus 2 squared. So that can factor into z minus 2 times z plus 2. You still have the z plus 1 in the problem, but that's the complete factorization of this problem. Something that you only recognize when you get down to that stage. Number 14 also looks like a difference of two squares, not cubes. First of all, there's no common factor here. Second of all, 49 and 64 are perfect squares. 64 is also a perfect cube, but 49 ain't. And b to the fourth, you can't cube something to get b to the fourth, not evenly, by the way. But you can square something to get b to the fourth. You can square b squared. So this is something that's known as a problem that's in quadratic form. It may not be a quadratic itself unless you make it appear as such. B squared squared still makes it work out. And this is still a difference of two squares, right? We just saw one. A squared minus b squared is a minus b times a plus b. Same thing here. This is a minus b times a plus b. Now, if this was a difference of two squares, we'd keep going, but neither of these are perfect square values, despite the fact that b squared is there. We will leave it as such. We are actually done on number 14. All right, 3 more questions, going pretty fast. Number 15, show that x plus 5 is a factor of f of x equals x cubed minus 2x squared minus 23x plus 60. Then factor f of x completely. I just look at number 13 as a recollection that I stated despite that quadrinomial was factorable by grouping, not all of them are. This is an example of a quadrinomial that is not factorable by grouping. So you'd have to find other means. Now, they're helping us because they're giving us a factor. So they're showing x plus 5 as a factor. Now, or they're not showing, they're telling us, they're saying we have to show it. This is where we can use long division. We can also use synthetic division. Now, before I go to synthetic division, let me show another way that you can show this thing's a factor. To be a factor for it, that means that its 0 would be an x-intercept. That when I substitute -5, right, if I plug in -5 here, I'm going to get 0 out. When I plug -5 into here, I must also get 0 out as a result. So here's one check you could do. It's not beneficial to our overall goal of factoring, but it does demonstrate that first part. So if you ever wanted to test it, -5 cubed minus 2 times -5 squared minus 23 times -5 plus 60. And I'll tell you what, I prefer this method if I can use a graphing calculator for it. Not that I have to punch all these in the calculator. It's when you're doing multiple tests to find out what a 0 is. We're going to save that for a future section. But I generally prefer synthetic division unless I'm using the graphing calculator. Anyway, -5 squared is 25 times -2 is -50. -23 times -5 is positive 115 and plus 60. This is -175 plus 115 is -60 plus 60 is 0. So it checks out that when you substitute -5, the official root or 0 for that factor, that you do get 0 out. That means it does it. Now they asked you to factor this thing completely. In order to do that best, once again, you would have to divide x plus 5 from this. You could use long division, but synthetic division really is the preferred way to go. And using either long or synthetic division, if you got a remainder of 0, you would also be demonstrating with that you do have, indeed, x plus 5 as a factor of this polynomial. So I could completely skip this if I wanted to, completely skip this, go straight to synthetic division, which bypasses all of your x's, as long as you rewrite them in standard form and you don't actually skip any of the degrees here, so degree 3, 2, 1, and 0. -5 is your root of this thing, and here's my visual version of it at least. Bring down 1, multiply by your root, -5, write it up here. Add these two, you get -7, multiply by -5, you get 35 here. Add these two, you get 12, multiply by -5, you get -60, and add these together, you get 0. Now, I'm not going to show you here why this works. I spent 42 minutes in a lecture for section 3.3 showing you why this works and how you do it. This is obviously the review for it, so I'm giving a slower demonstration. But the whys of the matter are saved for the section's lecture itself. Anyway, this becomes 1x squared minus 7x plus 12 with a remainder of 0. That was the division of this minus, or divided by this. Now, what we're attempting to do is factor this. So I can rewrite this polynomial as a combination of this times this. And that's what I'm going to do. I'm beginning the factorization. I didn't just divide out x plus 5. I factored out x plus 5. So f of x is x plus 5 times x squared minus 7x plus 12. And although the initial cubic we didn't know how to factor to begin with, you couldn't factor by grouping, now we have a quadratic that we could look to factor and is factorable. As a quadratic goes, we know to look for what two numbers multiply by this and add to this. And those numbers are -3 and -4. So x minus 3 times x minus 4 are the two values that go right here. This is the complete factorization of that polynomial. Now, once more, you could substitute -5 to check and see if you get 0 as a result, or you can use synthetic division to see if 0 is your remainder. Either of those are the show that x plus 5 is a factor. Using synthetic division brings you to your next step that you want to do, though, which is get to that quadratic after, or get to, a smaller polynomial after having factored out the thing you divided out. So it got you there a little bit faster. There we have it. Number 16. The estimated price P in cents of stamps in the United States can be modeled by the polynomial function P of T, hope we can use a calculator here, P of T equals 0.007 T cubed, P of T, hold on, minus 0.16 T squared, plus 1T, let's put a T, plus 17, where T represents the number of years since 1990. So if T equaled 2, that would be the year 1992. Use a graphing calculator to graph the function for the interval from years 0 to 20. Describe the behavior of the graph on this interval. Okay, We are going to go to the graphing calculator. Let's go and take a look at what to do. We're going to use x's instead of t's because we have no choice. Minus plus t plus 17. Okay, I don't know what kind of window range to look for. Let's hit the graph button, see if we can see the function to begin with. There it is. Well, I know part of our window range. We got to go from 0 to 20 on t, and it looks like we got to go a little bit higher up. Considering the plus 17 is our y-intercept on this thing, I'm in the wrong window. Considering the plus 17 is our y-intercept, I imagine I should probably have 15 in my window, 17 in my window range. I'll put 15 as a low end, and let's go up to maybe 30 and see what's going on in this thing. So I'm going from y values between 15 and 30. Maybe it goes down, I don't know. But I'm going from 0 to 20 on t. Let's see. Oh, not high enough apparently. Let's go and see where that was headed. So I guess it does go back down. Interesting. So let's go down to, I don't know, 5. I didn't really see it on the other part though. Ooh, that thing just goes right down. Let's make sure we wrote this thing right, because otherwise that doesn't really make sense from 0 to 20 unless there's something that we're not really using. 0.007. Oh, this is a cubed. Oh, I totally messed this up. Okay, let's try that again. Oh, okay, cool. That's in our window range. All right, then we get to see a good shoot up. Okay, my bad on the typo. Anyway, so we're looking at this graph. They ask us to describe the behavior of the graph on this interval. Now, keep in mind what this interval specifically means. The time is from 0 to 20. That literally actually means from 1990 to, I guess, 2010. So in the year 1990, we have the number 17. What was this about? Cents, the price of stamps in the US in cents. So the price in 1990 was 17 cents. And then as we go on, it barely increases, and then it kind of decreases. It kind of stays the same for this amount of years up until, I don't know what. The first 12 years up until about 2002, it's pretty stagnant. Then you start to see a slow increase over time over the course of the next 8 years. I think that's going to be my description there. Okay, next time type the thing in the calculator correctly, will you, Mr. Robinson? Anyway, so with this thing here, we can say the price of stamps from 1990 to 2002 was relatively stagnant, around 17 cents. I mean, it went a little up, a little down, but it wasn't much, right? But the plus 17 again is there. The last 8 years of this time period shows a slower, progressive increase in stamp cost over time. Now, what did it go up to about? What was my number here? Let's see, my window up to about 30, probably went up to around 30 cents by the year 2010. I'll say that. Up to around 30 cents. That's just from me looking at the graph. By 2010. What's the actual number? We'd have to compute them. I didn't spend time doing that. Part B. What was the average rate of change in the price stamps from 1990 to 2010? Well, hey, now we actually get to figure out what those numbers really were. We know that 1990 should be 17. You plug in 0 into there. 2010, on the other hand, we got to take a look. So average rate of change, I'm going to call this M. This is part B, because this is like a slope. We got to do y2 minus y1 over x2 minus x1. How much change over time did this thing grow per year? Remember, this graph kind of had like a, like that. We're just figuring out what this slope is right there. That's all. That's all we're trying to figure out. What's that slope? So I'm going to do P of 20. Going back to my calculator here. I'm going to go to P of 20. P of 0 is 17. P of 20 is 29. So, and it's exact. Wow, cool. Or is it? I guess so. Yeah, 29. Thank you. So this is 29 minus 17 over 20. 29 minus 17 over 20. The change goes from 17 cents up to 29 cents. That's 12 cents change over the course of 20 years. You increase 12 cents in 20 years. That's 3 cents every 5 years. That is 0.6 cents every 1 year, right? So What is the average rate of change in price stamps? 0.6 cents every year. Or whichever way you want to put it, right? 12 every 20, 3 every 5. Like that. That's on average, right? But that didn't really display what was truly happening in that time frame, right? You're averaging like this and say, oh, yeah, by the year, 1998, we expect it to be, this much, right? We expect it to be 5 cents higher. But it wasn't. It actually probably was just as much as it was at the time. And then it does a rapid increase. But that's just how averages work. And that's why we really want to fine tune them as much as we can. Okay, number 17. The volume V in cubic feet of a rectangular wooden crate is modeled by the function v of x equals 2x cubed minus 11x squared plus 12x, where x is the width and feet of the crate. Determine the values of x for which the model makes sense. Explain your reasoning. Let me get a better version. I think that one is better to not be blurry, so hold on. Let me pick up this guy right here. It even has the problem written on the original thing. So let me also go to the next page. Okay. Wow. Let's bring it in. Let's reel you in, big guy. There you are. You ready? You ready? Okay, here we go. All right, so for number 17, we have this. Now they said, explain where the model does make sense when it comes to volume. Well, one place it won't make sense, whether we're talking about x or v, is negative stuff. Negative lengths or expressions for length and negative volumes definitely don't apply there. But negative volumes shouldn't really apply anywhere. The only places that we really should apply is positive volume. Positive volume here and positive volume here. Now, our goal to determine positive volume is also to determine what these x-intercepts are. I think it's safe to say, for several reasons, that this is an x-intercept of 0. Not just by visual, but also by the fact that x is a common factor. V of x equals, you can factor an x out, and you're left with 2x squared minus 11x plus 12. Now, there's another x-intercept that's seemingly correct as well. 1, 2, 3, 4, x equals 4. There are a couple ways we can check on whether x equals 4 works or not. We can use we can plug in 4 into here and see if we get 0. We can use synthetic division if we get a 0 remainder, which is a nice one. You can also, so you can do this for checks. You can also attempt to factor this quadratic on your own. Let me actually begin with the quadratic factor check, and then we'll go about other businesses, because we got to find out this number, which I imagine is probably 1.5, but let's see. I don't know. I don't know for sure. It just looks like it is. So if this is factorable, this would be some sort of 2x times x. And then 12 can be comprised, now that I know that 4 should be one of my intercepts, I should really try x minus 4 right here. Given that it's a positive product, negative sum, both would have to be minuses. What times what is 12 in this case? Negative 4 times negative 3. So let's see if that works. This is 2x squared minus 8x minus 3x. Yep. And then plus 12. So this is the best factorization of it. And therefore we have x-intercepts of 0. Add 3 and divide by 2 to both sides. You get 3 halves. That is 1.5. And then this last one here is 4. So that's a way you can get those x-intercepts, which we'll need. You can do it by factoring. Once you found the common factor stuff, we honestly don't need the graph for the factoring. What we do need the graph for is to determine where it's positive or not. But before we talk about that, now that we have those numbers, let's also find those numbers using what I was talking about before, synthetic division. Now, let's assume that that x was already factored out and we're only talking about this quadratic right here. 2x squared minus 11x plus 12, and we test 4 as a root. We test 4 on here to see that we get a 0 remainder. We will, and we're not surprised by the fact that we get it. The test is more a test of assurance, not test of like uncertainty. So bring down the 2, multiply by 4, add those together, multiply by 4, and add those together. And you end up getting now, remember x was already a factor. If 4 is a root, that means x minus 4 is a factor. So x and x minus 4. And then the last one is what you're looking at right here, 2x minus 3. And that brings us back to what we were talking about before, x times x minus 4 times 2x minus 3 all appear here. This is where you get these x-intercepts. So that's not the answer. The question is, which values of x make the most sense when it comes to volume based on the function that you're seeing here? We want the values of x where we have positive volume values. So anything to the right of 0 and to the left of, remember that's 3 halves, anything between 0 and 3 halves seems to be valid x values for which you'll get positive volumes. And if x is greater than 4. So it's really a matter of factoring and kind of choosing your own adventure when it comes to how you want to get the factoring done. But that's what's going to get you there because these are positive volumes. That's my reason I am stating there. These are positive volumes. Anyway, as you probably well know, there are so many different kinds of questions that you can be asked in these 4 sections. I mean, the average video length of my things was probably close to like 2 hours, 20 minutes or something like that when you consider them all. So there are clearly a lot of different questions to be had, but this is a pretty good review. We didn't do any graphing ourselves, but we will dive into more graphing by the tail end of this chapter for sure, in a way that you're probably expected to graph these in the future. Doing a lot of what we're doing right now, a lot of things, the factoring, synthetic division will be used, using intercepts and do things. We didn't get to talk, you know what we didn't get to talk about though, were things like end behavior. You know, how the leading coefficient and the degree being even or odd changes those things. So if there's something to still look up and practice, I'd say the end behavior stuff. The drawing a graph or understanding a graph based on that and leading coefficient. Leading coefficient and degree determining end behavior. All right, guys, that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. Next will come up 5 more sections in the chapter. We go all the way to section 3.9 on this, so get ready. We got more to do. Take care. Thank you. I'll see you in the next one.